Alright, so we're going to talk about acceleration today, and I'm going to start with an easy question. Maybe your international students may not be familiar with The Grinch Who Stole Christmas, but it was a favorite at my house when the kids were younger, and we watched it every night for about 6 weeks in a row. And there was always one part that made me laugh, maybe not after the entire 6 weeks, but when the Grinch's dog, whose name is? Gotta start the question, which I just did. So, who remembers what the name of the Grinch's dog was?
Hey, Joel.
Joel was not the Grinch's dog's name, Jason. You guys know the Grinch movie? No? Yeah? Okay, just guess. Just for fun. It's okay, Matt. Don't worry about it. Okay. What is it? Yes, it's C. Max. Right? Sans little helper, of course, from The Simpsons. Buster was my dog. Fido was Mary. Right? So there's a scene in the Grinch where the Grinch puts the antlers right on the dog, trying to make it look like a reindeer, and he's sliding down the hill, and the dog goes so fast, right? Or no, the Grinch goes so fast that he catches up, and the dog goes around like this, right? Defying physics. So I always think of that when I start talking about acceleration. So if I ask you right now, before I get that question, if I just ask you what does acceleration mean, who would like to take a wild run at that? If I say, what is acceleration? Okay. So I got no volunteers. You're sitting there smiling, you're happy. This is going to make your day any worse. What does acceleration mean?
Acceleration is like when you're like you speed, like you start like you're stopped and then you go like it isn't a constant speed, like you're going you speed up.
You're speeding up.
Yeah.
Do you have to be speeding up to be accelerated? Yes? Otherwise you're slowing down to decelerate. Okay. What if you're just like changing direction? Is that acceleration? Like what if I'm doing this? What if I got this rubber stopper over my head? I gotta be careful because it's a concussion point. And it's traveling at a constant speed, say 5 revolutions per second. Is it accelerating, Jason? No? What do you think, Wayne? I've heard of you. Not accelerating, or it is accelerating?
Well, how does accelerate to get up to speed?
Okay, yeah, well, once I get it up to speed. Not accelerating. Okay. Okay. Well, let's talk a little bit more about that. Oh. I didn't do that yet. I accidentally showed the answer, I think. So acceleration is, like velocity, a what kind of quantity? Is it vector or scalar? Well, you should know that velocity is a what? Vector or scalar. So what about acceleration? Because it says it's the same. Velocity is a vector, and so is acceleration. Velocity. And if it's a vector, that means that it has a direction. We all need a little direction in life, don't we? It's a direction. There has a direction, which means it's a vector. So that means that acceleration is a vector. It has a direction. So when I'm spinning this around in my head, right, am I changing the direction? certainly am. At some point it's going east, and then it's going north, and then it's going west and south and so on. It's changing direction. If I'm changing the direction, that means there is an acceleration. More on that in grade 12, in the circular motion sense. So acceleration can be positive acceleration, which means to the... I believe you can answer more than one here. I think you can. You should learn how to check that. Yeah. You can answer more than one. Positive acceleration could mean to the left, to the right, to the up, or to the down, or more than one. You can answer more than one. B and C is correct. Right? Up and to the right. Positive acceleration. Now, please, come on, you guys. Let's get this next one right. Can be negative to the left, to the right, to the up, or to the down. I think I gave the answer right, didn't I? I was in answer mode instead of questioning mode. Oh, you all are going to get this right, aren't you? Aren't you? Make my day. B and C, says Jason. Get a man good there, Gerard. Not B and C. A and D, acceleration is left and down. Okay, now here's Trent's question, or Trent's, yeah, I guess Trent's question. So the question is, does deceleration always mean slowing down? Bit of a trick question. Does deceleration always mean slowing down? Tough question. Well, you might want to jot some of this down here. So acceleration to the left is sometimes called deceleration because if it's negative, it was Trent who said deceleration is negative, right? But be careful does not always mean slowing down. Okay? Because, for example, what if I'm already, here's a three-body diagram, what if I'm already traveling to the left? Let me start over here on the right, your right. I'm starting over here and I'm going to my left at 5 meters a second, and then I speed up, my acceleration is this way, but I'm speeding up, aren't I? Right? So, when the velocity and acceleration are both in the same direction, then you're speeding up. I need to pause there, I can sense. Okay, so acceleration to the left sometimes called deceleration, but it doesn't necessarily mean slowing down, because if I'm already going left, let's say -5, and I accelerate to the left, then I will actually speed up. So the rule is this, right? If the velocity and the acceleration have the same sign, like if they're both positive, then it's going to speed up. If it's opposite signs, then it's slowing down. Okay? So what I'm really getting at here is that I'm going to try to avoid the term deceleration. Any change in speed is an acceleration, whether it's positive or negative or change in direction. Okay? Try not to use the word deceleration in a physics class because it can be confusing. So let's just always go with acceleration, and negative just means to the left. And negative acceleration doesn't always have to be a slowing down. That's what I'm really getting at here. Okay, so I asked you at the start, what is acceleration? If you haven't written anything down now, that's okay. Oh, by the way, I handed this out. I should explain. I didn't. In these notes here that I'm going to do, there's some graphs. To make it simpler, I just handed you the graphs. If you want to leave spaces and cut them out, tape them in, or glue stick them in, or if you want to just do your notes on here, or write your notes on the back, I don't care. Do what you need to do so that when you're looking back at this, it makes a little bit of sense to you. If you want to just sit back and enjoy and then print out your notes at home, you can do that too, because as always, I'll post these to Schoology. So, acceleration is properly defined as, in physics terms, and sort of that kind of scientific language, it would be the time rate of change in velocity. Now that doesn't mean a whole lot to grade 11 students. Time rate of change in velocity. So underneath the cover here, I've re-explained it a couple different ways. So, what might be another way to explain time rate of change in velocity? Lane was right. She was talking about car speeds up at a red light, right? Let's say you're at a red light. Lane's got a BMW, and I got my minivan. Who's going to have the greater acceleration? Because I'm driving? Yeah, right. Probably not. Is it automatic or is it a standard?
Automatic.
Of course.
Yeah.
Lane stalled. Okay, I stalled in a race, but I still beat her.
You what?
I stalled in a race against her, but I still beat her, so.
Is it really standard? Wow, so you had to do some heavy duty learning. I remember the first time I learned how to drive stick, it was a little ugly. A lot of the guys laughed at me. Good for you. I'll tell you a story in a while. Okay, so anyways, Lane's BMW probably has a greater acceleration. I don't have a minivan. I didn't want to bring anyone. I didn't want to say, who doesn't need that? Don't get it.
I do.
Do you?
Yeah.
Okay, so how would your minivan stack up against her BMW? Okay. Would she be like, beat you to the next intersection?
That would be fast.
Probably, right? Yeah. What does that mean to have a greater acceleration? It means that she gets up to speed faster. If it was a semi and a BMW, right? The BMW is going to get up to speed faster. It has a greater acceleration. It can change its speed faster. So acceleration is simply how fast an object's velocity is changing. How fast an object's velocity is changing. And it could be speeding up or slowing down. Any defensemen back here? Any of you guys defensemen? Okay. So you're taking the slap shot from the point there, right? Right? How fast does the puck go from 0 to what, 100 miles an hour?
Where's she going?
Come on, just so let's say 80 miles an hour, right? So you slap shot 80 miles an hour. How fast does it go from 0 to 80? It goes really fast, right? Really? 1 second? Way less than. Okay, let me ask you this. If it hits the goalie's pad, how fast does it slow down to 0? Faster than when you... Really? Oh, the pad absorbs it. Oh, okay, you might be right. Is either one of those acceleration? The speeding up and the slowing down? They're both acceleration. One's positive, one's negative, that's all. So how fast an object's velocity is changing, or if you prefer, how fast is an object's velocity increasing or decreasing? Note that I haven't said anything about direction. How fast an object's velocity is increasing or decreasing. If you prefer, how fast you get to how fast you are going. That's a little confusing. How fast you get to how fast you're going. Don't write it down if it doesn't make sense to you. Did I show you guys the video with the motorbike and the plane? Did I show you that yet? No. Okay, good. We'll get to that. We might even meet today. I really should look at these ahead of time so I know what's coming up. How fast you get to how fast you're going. Do you know, now after all this, what the equation for acceleration would be? Given that acceleration is how fast you are changing what do you think that the equation for acceleration is? Now, some of you, depending on your grade 10 teacher, might have taken this. That's fine. But you certainly need to know it here in grade 11. So is acceleration equal to delta D over delta T, D bar, which is average over delta T, V bar over delta T, or delta V over delta T? All a little bit confusing, I understand. You can guess, that's fine. Really, the clickers are just my way of making sure you're paying attention every once in a while. The acceleration is how fast you are changing your speed. The answer is, we're all over the place, but the answer is D. Change in velocity divided by change in time. Make sure you have that written down at some point, right? It's change in speed over change in time. Acceleration is change in velocity over change in time. I guess you got it down there, right? That is the formula you're going to have to use. Now, I can say that as many times as I want to. I still find that students have a hard time really understanding what I'm talking about. This will be a long process. There's grade 12 students that still, I can tell, they can regurgitate it back to me, but I can tell that they're not really getting what acceleration is. So we're going to be spending our time over this. Here's the first graph that we've got there, right? Now, we've done some of this already, so it shouldn't be too challenging here. In the graph below, the displacement graph is a curved line, meaning that the velocity is it decreasing, increasing, or staying the same? If you completed the lab the other day, you should know this. We've got a curved displacement time graph. What does that tell me about the velocity? Is it decreasing, increasing, or staying the same? Do we get it? It is increasing. Why? The slope is changing. In fact, the slope is not only changing, the slope is getting steeper. Right? Here the slope is flat, there it's steeper, there it's steeper, there even steeper. The slope is increasing. Keep in mind, this is a position time graph. We'll be getting into velocity time graphs next week. Okay, here's the hardest one we're going to have today, probably. Since the velocity increases at a constant rate, the velocity graph is a what kind of line as shown below. So which one of these is the matching velocity time graph? These are all VTs. This is a position time graph. Which one of those, A, B, or C, is the matching velocity time graph? I'll wait a little longer for this one because this one might take some thinking on your part. VT graph is a graph of the slope of the PT graph. Okay, I'm going to explain that right away. Okay, so what I mean is, if I were to take the velocity at, say, 4 or 5 different points, if I were to find the velocity right there, I'd find the slope and come up with some number, like maybe 1. And then I find the slope here, and the graph slope might be 2, and then I find the slope there, and it might be 3, and then I find the slope there, and it might be 4. We're taking, guys, Trent, we're taking the slope at 4 different points, and then we're going to graph them. 1, 2, 3, 4. Does that make sense? This is a graph of the slopes of this graph. The velocity time graph is a graph of the slope of the PT graph. Okay, now what does it have to do with acceleration? The acceleration graph is a graph of the slope of the velocity time graph. Acceleration is a graph of the slope of the velocity time graph. In other words, if I do the same thing, if I find the slope at 4 different points on a VT graph, that is my acceleration graph. If I go back to this, what's the slope at those 4 different points? Some number, right? Is it the same? Is the slope there the same as the slope there? Is the same as the slope there? Is the same as the slope there?
Yeah.
If the slope of that graph was 0.4, that tells us that the acceleration is a constant 0.4 meters per second squared. And I'll explain that meters per second squared right away. So if I find the slope of that graph, and I found it to be 0.4, this tells me that the acceleration is a constant 0.4. What's the shape of the acceleration time graph going to be like? What's it going to look like? Do you have it on your sheet? I think you do. What is the shape of the acceleration time graph? It's going to be flat. Right here at 0.4. The shape of the acceleration time graph is a flat at 0.4. We would call this uniformly accelerated motion. What does the word uniform mean? It means that it stays the same. Uniformly accelerated motion. Okay, so let's put Cameron's minivan and Lane's BMW on the starting line again. Lane, when you shift from first to second, what do you have to do? Put the clutch in, right? Shift gears, right? Does your car continue to move during that time? Yes. Does your car continue to speed up during that small window of time? No, because putting the clutch in disengages the gear shift, right? The gear. And so you're not accelerating at that time. The faster you do it, the faster you get going acceleration, right? So every time Lane switches gears, right, there's that momentary stop in acceleration. Would that be uniform acceleration? No, it wouldn't, because you'd be constantly changing, right? Now, Cameron's got her on that. She just puts her foot to the metal and to the pedal and just gives her, right? Obviously, it has to change gears as well. Is there a small little change in acceleration there? Small, but not near as much as there is on a stand, right? Because it's not automatic. You go into those new fancy, what do they call them? Where there's no, not the paddle shifts. Some of the Dodges have it. Like a variable speed transmission or something rather, or there's no gears. It's just like there's no gears. Yeah. What is it called? CVI? What does that mean? Do you know? Oh, yeah, I don't know. I know Mr. Drosh has it because it's weird. You don't feel that sort of change in gear count. Okay. Now, you should have this one as well. This graph. This velocity time graph is an example of variable acceleration. Variable simply means that it is, well, I'm going to give away the answer, but I think that's it. But acceleration is not constant, it could be constant or not. I'll tell you what, it's not C. Variable acceleration. How we do? Oh, not constant. That would be like the graph of when lanes shifting gears, right? Okay, it varies here. Okay, here's another thinking question. Does this object ever move backwards? Yes or no? Does this object ever go backwards? I want you to draw a velocity time graph with a similar shape that does show the object moving backwards. How would I draw that? What would I have to do on my VT graph to make the thing go backwards? Go into the negative? Like that? Yeah? Or what about like that? Which one of those would be going backward? Say again, Zoe? The second one, the black one? Why? You can't start at a negative speed? Yeah. Usually we put 0 at the start, right? You're right, Jason's right. This one starts at 0, right? The car, we've been talking all along about these cars on a road at a stop sign, right? This one here, you would have to actually be already going backwards when the time starts. This one actually shows you going backwards. It's quite unlikely because you'd have to already be going backwards. Then you would actually stop going backwards. Then you would continue to go backwards and then come back to stop again. This one shows you actually going forward, slowing down, stopping, speeding up, and then slowing down. In fact, you know what? Let's do this. I think this might be a good chance for me to do this. How big did you guys make this graph? Not very big? I'm just going to make it bigger so that I can draw on it. This part here is speeding up. This part here is slowing down. What's happening right there? For how long? Just an instant, right? Okay, what's happening here? Speeding up again? Forward? Backward. Speed up backward. That's good. Speeding up backward, and this one here would be? Exactly, slowing down backward. So notice here, what's the slope here? The slope here would be the acceleration, right? Is the slope here positive or negative? Positive. Slope here? Positive. Positive slope speeding up, positive slope slowing down. How can that be? One's going forward, one's going backwards. Exactly, right? I will tell you this. When you're doing these kind of questions, when you see graphs and all this, you're going to have to just pause, check the kind of graph you're looking at, and really think it through. Don't go with your gut. Your gut is often right, but think it through. Take your time. Okay? Okay. Notice that the slope of the curve is not always positive. I think that's what I was getting at here. Again, forget what's coming up on my slides here. Let me just look ahead here so I know what I'm talking about here. Right. Lots to talk about today. I apologize for this being not the most entertaining day. Between points A and B, let's find the slope between these points. Would you say that A right here, what's the value of A? 4. And the value here at B would be 2, which means that the delta V, the change in velocity, would be minus 2, right? The velocity changes by 2, negative 2. And that all occurs in how much time? 1, 2, 3 seconds. So we would say that the acceleration is delta v over delta t, 2 minus 4 all over 7 minus 4. The acceleration is minus 0.67 meters per second squared. And I promised I'd tell you what that square meant, and I'm going to do that right away here. That would be the average acceleration here. The slope of that line. Color it in so it makes it look straight. So the acceleration is minus 2 over 3, or minus 0.67 meters per second squared. Okay, so let's talk about units here. I would just, you know what, put your pencils down, don't write, just listen. I'll leave time at the end to get you to write down, okay? Just take a writing break here. Notice the units on acceleration, meters per second squared. It's important. I will circle that on tests if you just put meters per second, okay? Meters per second squared. Acceleration is the rate of change of velocity, which is the rate of change in displacement. In other words, A is delta v over delta t, right? But this delta v, circled in red, is made up of d over t, right? So it's delta d over delta t over delta t. There's two versions, two instances of the delta t. If I were to do it in units, and don't freak out here, I get kids that freak out, they have seizures and everything. Don't freak out on me. Okay, so using units, what is, let me see if I can line this all up here. What do we measure? What unit do we use for delta t? Meters. What unit do we use for t? Seconds, seconds. So I got meters per second per second. Meters per unit, or meters per second per second. Now, do you remember how to divide fractions from like grade 7 or 8? How do you divide fractions? No, that's adding. You're in the right ballpark. You got the wrong date. You're right at it. You flip which one? You flip the second one and you change it to multiply. You flip the second one and you change to multiply. So the second one here is seconds. Well, it's really seconds over 1. So I'm going to take meters per second, divide by seconds over 1. And as Anna says, you flip the second one to multiply. So now the seconds over 1 becomes 1 over seconds. So I got meters per second times 1 over seconds. And how do you multiply fractions? You go straight across. So meters times 1 is meters, and seconds times seconds is meters per second squared. That's why it's meters per second squared. You don't need to be able to regurgitate that back. Okay? You just need to know that acceleration is meters per second squared, and for those of you that want to know why, that's why. Okay? Sometimes they'll just say meters per second, but meters per second squared is the proper unit for acceleration. Okay, I got a video for you right away. We're running out of gas here and time. So this dude here, Galileo, you probably heard of him. He was the first scientist to clearly understand the concept of acceleration. He did some major league experiments. We're going to try one. You're going to get a better appreciation for the challenges that he's faced. Okay? So Galileo found that the acceleration of a ball rolling down an inclined plane and the acceleration of a falling object were both described by the same mathematical rules. So he built a very long ramp, made it very smooth to reduce friction. Are there still ramps there? You guys get me down one of the ones with the group, the big ramps? What do you guys? You can reach it. Don't hit your head though. Just bring it up here for me, would you?